Today we will be looking at integration. Integration is another aspect of calculus. We have already discussed differentiation. In our discussion today on integration, we will start by looking at the indefinite integrals. Indefinite integrals. Integration is the reverse or inverse of differentiation. The symbol elaborated S is used to represent integration. In other words, if we find the product of differentiation times integration to be equal to 1, and if you now integrate a differentiation, you have the function y. Or if you now integrate dy is equal to the function y with respect to s. This is equal to f of s ds. Now, the indefinite integral f of s ds is a function f of s plus c. That is, when you now integrate this, you will have this new function. And the c here is an arbitrary constant. In other words, when we carry out integration, there is always a constant and c, and we determine that constant c if given other necessary information. If you differentiate f of s plus c, what do you get? You will get the integrand f of s ds. So that is, you can move from differentiation to integration, and from integration back to the function differentiation. That is to say, if you differentiate this function f of s plus c, you can notice that I'm using a capital F to differentiate this one from the small letter f that we use for a function. Though this is a function, but it's a function that was begotten from the function f of s here, the original function. So we have derivative of this function is also equal to the original function f of s. In general, if you are to integrate a function s raised to the power n with respect to s, this will be equal to s raised to the power n plus 1 divided by n plus 1 again, and then plus the constant of integration k. K, as I said earlier, or c, as sometimes used by some authors, is the constant of integration. Let's take the first example. Number 1. Integrate s cubed with respect to s. Our solution, we have the function s to the power 3 ds will be equal to, applying the formula, add 1 to the power s to the power 3 plus 1 and divide by the sum of the power, which is 3 plus 1. And then you will add the constant of integration, which is k. So that this will give you s raised to the power 4 all over 4 and then plus k. And that is the solution. Number 2, integrate 2s all raised to the power 3 ds. This time I've added a constant as a coefficient of s cubed. And here, in this regard, you can actually write this as 2 in our solution, integrating s cubed with respect to s. All I have done in this case, different from the former case, is that the constant 2 is brought outside the symbol, and then you can go ahead and integrate s, and this is 3 plus 1, and then all over 3 plus 1. Remember that this is, and then plus the constant of integration. And then that will give you 2 into s to the power 4 all over 4, and then plus the k, so that the 2 will cancel 4 to give you 2. So the final result will be equal to s to the power 4 all over 2 plus k. Or you can write this as half s to the power 4 plus k. Now, if y is equal to 3s raised to the power 4 plus s squared plus 5, if we have this case, then our dy all over ds here will be equal to 4 times 3, which is 12, and then reduce 4 by 1, s to the power 3, plus 2 times s reduced by 1 will be 1, that is s, and then plus 0. This, of course, is the derivative of the function y equal to 3s to the power 4 plus s squared plus 5. Now, if you integrate our 12s to the power 3 plus 2s, now with respect to s, now what will you have? You will have this as the integration of 12s cubed ds plus the integration of 2s ds. Going further, your 12 is out, and then you have s cubed with respect to s. Your 2 is out with s with respect to s. Then we have 12 here, multiplying. If you integrate this one, you have s to the power 4 all over 4 plus 2. If you integrate this one, you have s to the power 2 all over 2. The result is 3 s to the power 4 plus s to the power 2, then plus the constant of integration. Now, if you look at this carefully, before I added the constant of integration, if I've ended it in this form, and the original function y has a value plus 5, so we will have lost that value. And in order to regain that value, we have to add the constant of integration. And given some other information, you can find even the value of k, as we shall see in subsequent examples. The properties of indefinite integral. The first property is derivative of an integral u ds is equal to u dx. Reason derivative or differentiation is the inverse of integration. So d and this symbol will cancel to leave you with u ds. Number 2, the integration of du is equal to u plus c, where c is a constant. It's like when you are told just integrate a constant, and then the integration of that constant is in terms of u will be u plus c. 3, the integration of k u ds, k is a constant, so we have k here into u ds. So you bring out the constant, as I said earlier when we were discussing the integration of 2s cubed. We brought out the 2 and then we integrated s cubed. This is exactly what we are saying here. The fourth one is, if you are to integrate some u plus v ds, integrate them separately 10 by 10. So integrate u ds and add it to the integral of v ds. Let us take a look at some trigonometrical functions. Number 1, the integration of sin s ds. This will be equal to minus cos s plus the constant of integration. You will recall that in differentiation, if you differentiate cos s, you will have minus sin s. So now, if you differentiate minus cos s, you have plus sin s. That is why the integral of sin s ds is equal to minus cos s plus k, the constant of integration. Number 2, integration of cos s ds. This will be equal to sin s plus k. This is a situation where if you differentiate your sin s from what we have done earlier, the answer is cos s. So if you integrate your cos s, the answer is sin s plus the constant of integration. The third one, a little bit different from what we have done. This one is 1 all over s ds. To integrate this function is equal to the log to base e of s plus k. The log to base e of s plus k. So we can put e here if we wish to. Alright. The fourth one is the integration of e raised to power s ds. This is an exponential function. Exponential function. In this case, this will be equal to es plus k. Whereas, if we have to integrate e raised to power 2s, for example, e raised to the power 2s ds, this will be equal to half of e raised to the power 2s plus k. Still under the trigger functions, if you have a case like this, you are asked to integrate tan s with respect to s. You are told to integrate it. You will recall that tan s is the same thing as tan s all over cos s with respect to s. Now, there is a function here. The answer, let's give the answer first. This will actually be equal to minus the logarithm of cos s and then plus the constant of integration, which is k. Now, why have I written this? The obvious reason for this is that there is a principle or a rule in integration which says that if you integrate a function which is given to you like this with respect to s, now this function at the denominator, if you differentiate this function and you get the numerator, then the answer to this problem will be equal to the log of the function f of s plus the constant of integration. It is this rule that we have used in solving the problem of integrating tan s, where tan s is equal to tan s all over cos s ds. But somewhere along the line, there is a little modification that we have done. We know that if we differentiate the s of cos s, if you differentiate this one, you will have minus tan s. So in other words, all we need to do to that integral is to write that this is now minus tan s all over cos s ds. So we have included the minus there, which we can actually bring out, and then we have this. So if I differentiate this, I will have tan s times this minus, which is minus tan s. So the result is equal to the value we have minus the logarithm of cos s plus the constant of integration. Take note of that. Sometimes commonly the questions will just come and you can simply solve it the way I have discussed it now. Now we have an example under this discussion to integrate 1 minus s all over s cubed with respect to s. Now our solution in this regard to integrate means you have the symbol 1 minus s all over s cubed with respect to s. Now we will do this 1 all over s cubed minus s all over s cubed, and of course with respect to s, so that this will of course give you your s raised to the power minus 3, integrate that, the s minus, this is 1, s will cancel one of the s here, so you are left with 1 all over s squared with respect to s. And as a matter of fact, we can simply just write this one as s raised to the power minus 2. So now what do? You add 1 to minus 3 to give you s raised to the power minus 2, and then you add also 1 to that, of course divided by minus 2. And here you do the same thing, that will become s raised to the power minus 1 all over minus 1. So that you simplify this to give you your minus 1 all over 2 into s squared. Remember your loss of indices, and over here minus will be plus, and then we have 1 all over s, and then plus the constant of integration. And I think that is the solution to this problem. It's correct. Here's another example, example 2, under this topic. Integrate 1 all over s plus tan s with respect to s. Your solution, we want to integrate 1 over s plus tan s with respect to s, and that will become the integration of 1 over s with respect to s plus the integration of tan s with respect to s. And of course, if you differentiate s, you get 1. So this becomes log s. And then what will you differentiate to get sin s? Minus cos s. And then plus the constant of integration. We look at change of variable. Under change of variable, we are going to be using the substitution method. So we say we use the substitution method. We use the substitution method. And then we take an example of what we're saying. And the example is evaluate. What we have here is sine 3s with respect to s. Now, in our solution, we will say let u be equal to 3s. In other words, our du all over ds is equal to 3. So that our du is equal to 3 times ds. Therefore, our ds is equal to du all over 3. Take note of this, that's the first step. So we will replace our ds by du all over 3. After we have made u equal to 3s. So we now have the integration of sin u, because 3s is now u, and our ds is no longer ds but now du all over 3. Then of course this 3 can be brought out as 1 over 3, the integration of sin u with respect to u. And of course, what does this give you? 1 over 3. What do you differentiate to get sin u? You differentiate minus cos u. Of course, and this will be equal to minus 1 over 3 and then cos u. What is our u? Our u is 3s. And then plus the constant of integration. You will have integrated sin 3s ds. Under the same change of variable, let us look at another example. Evaluate 2s minus 3 all this power 2 over 3 dx. Our solution, again, let your u be equal to 2s minus 3. So that our du is equal to 2 times ds. Therefore, ds is equal to du all over 2. Now, it means we have s, our u now, raised to power 2 all over 3, du all over 2. So that will be equal to half integration of u raised to power 2 all over 3 du. Now, if you have this, remember your the rule for integration, so that will be actually equal to half, add 1 to 2 over 3 to give you u raised to power 5 all over 3, divide again by 5 all over 3, and then plus the constant of integration. Now let's go simplifying. We have half multiplying 3 all over 5, and then multiplying u, and our u is 2s minus 3 all raised to power 5 all over 3 plus the constant. So this simplifies further to 3 all over 10 into 2s minus 3 and then power 5 all over 3 plus the constant of integration. And that gives you the solution to that problem. Another example, example number 3, find the integral of 3 cos 2s minus 2 sin s. Our solution, we have here the integral of 3 cos 2s minus the integral of 2 sin 2s. We can take them 10 by 10. And then of course, this with respect to s. If I even remove this, you can have it in this form to start with. So we can now separate by writing this as 3, the integral of cos 2s, then we have minus 2, the integral of sin s, and then of course all with respect to s. Now, this done, we have this as 3. From the knowledge of the sin 3s that we integrated earlier, we will also do something here. So what do you do? This one becomes half, and then what do you differentiate to get cos 2s? You differentiate sin 2s. So this is sin and 2s. And then here we have minus 2. Then what do you differentiate to get sin s? You have minus cos s. And then when you simplify this to give you 3 all over 2 sin 2s. Minus times minus is plus, and this is 2 cos s plus the constant of integration. Example number 4. If dy over ds, the derivative of a function is equal to, of a function y is equal to 1 over 2, that is half, into sin 4s plus sin 2s plus 1. Find y. Solution. For us to find y, remember you are given dy over ds. So you integrate your dy all over ds, and then this will be equal to the integral of half of sin 4s plus sin 2s plus 1. So that the integral of the y is equal to the integral half of the integral of sin 4s plus sin 2s then plus 1 ds. Good. So your integral will cancel your derivative, giving you y equal to your half, open the big bracket, you do integrate the function here 10 by 10, so we integrate our sin 4s with respect to s, we will integrate our sin 2s with respect to s, then plus we will integrate our 1 with ds. So in this regard, we have here our half into, if you integrate sin 4s, you will have 1 over 4. Then what do you differentiate to get sin? You differentiate minus cos, so minus cos 4s. And then for sin 2s, the same thing, we have this as plus half, and then what do you differentiate to get sin 2s? You differentiate minus cos 2s. Close that. Plus, we have 1. 1 there means s raised to power 0. And so if you integrate ds, what do you have? You have the value x. So as far as this case is concerned, everything here under the square bracket. So we simplify this as half into minus 1 over 4 cos 4s minus 1 over 2 cos 2s and then plus s. So multiplying through by half, we have minus 1 over 8 cos 4s and then minus 1 over 4 cos 2s and then plus half of s plus the constant of integration. You will find the value of our y. So our y is equal to that. Another example is example number 5. Evaluate the integral ds all over s into s plus 2, where s is not equal to 0 and s is not also equal to minus 2. Solution. I want you to observe critically the denominator of this function. The denominator s into s plus 2 is linear in terms of our partial fraction. S is linear, S plus 2 is linear. That's exactly what I mean, not the product. Now, with what we have in this case, you will now discover that it is the application of partial fraction that will help us to integrate this particular function. That is why in the study of partial fraction, we are told that the application of the partial fraction is in the area of integration. And this is one of the examples of how to use partial fraction to integrate algebraic functions like this. So in this regard, we first of all break our function into partial fractions. We decompose it. And so what do? We have 1 all over s into s plus 2 will be equivalent to a letter or yes, a letter A all over s plus another letter B all over s plus 2. For this particular case, this is how to decompose it. Now that we have done that, we multiply through by the common denominator, which is s into s plus 2, leaving us in the left hand side with 1, and then s will cancel s, leaving you with A and s plus 2 with the first term, and then s plus 2 will cancel one of the terms, leaving you with s multiplying the letter B. Now, what we need to do is to find the value of A and B. And the simple thing we can do is we can now put our s equal to 0, for example. So here there is no 0, so 1 will remain. S is 0, so we have A times 2, which is 2A, and s is 0, 0 times B is 0. In this regard, we can therefore have our A to be equal to 1 over 2. Similarly, you can see decide to put your s equal to minus 2, because when you do that, one of the variables, A or B, will vanish. In this regard, which one will vanish? There is no s here, so 1 will remain. Here is minus 2. Minus 2 plus 2 is 0, so A will vanish, and then we multiply this by minus 2, and that's minus 2B. Our s is minus 2. So, therefore, we have that our B is equal to minus 1 over 2. So, the expression, therefore, ds all over s into s plus 2 will now be equivalent to the expression which says our A is half, so 1 all over 2 s, and then the next one is our B is minus, so minus 1 all over 2 into s plus 2. Good. So this is now what we are going to integrate as far as this case is concerned, all with respect to s. So if we have done this, we can now take them term by term. So this becomes half the integration of 1 all over s, and then minus half again the integration 1 all over s plus 2, all with respect to s. So if you do this, remember, if you differentiate s, you have 1. Therefore, this will give you half log s, then minus half again. If you differentiate s plus 2, you will have 1, because the derivative of s is 1. So this is again log s plus 2. And then plus the constant of integration. This gives you the solution. In some cases, we can go further to rearrange this using the theory of logarithm, where your minus becomes a division. But let's leave it at this as a solution. Or you can have a half here into the logarithm of s divided by s plus 2, and then plus the constant integration. From the theory of logarithm, subtraction meaning that divide s plus 2 into s, and that's what I've written here. Half was common, so that gives us the solution. You can see the solution in this form, you can also see it in this form. Even in some cases, they can go further and write this as log of s all over s plus 2 in brackets, and this half becomes a power, but it is also okay in this level. Example number 6. Evaluate the integral of 4s squared all over s cubed minus 7 with respect to s. Now, our solution, if you take a look at this, if we differentiate 3s minus 7, we will have, now let's do it, the derivative of s cubed minus 7 will give you 3s squared. And of course, the numerator has s squared, and it's also having a 4. So we can then do some manipulation like as 4s squared all over s cubed minus 7 is actually the same thing as 4 into s squared all over s cubed minus 7. Now, I know that when I differentiate this, I will have 3s squared. So, I can simply write 4 into 3s squared all over s cubed minus 7. But what? So, the only way that this expression can be equal to this one is that I also have to divide by what? The 3. So, if I multiply this by this, 3 will cancel 3, and then we are back to the 4s squared that's supposed to be there. In this wise, we can carry out our integration, and we now say that it is equal to 4 over 3. When you integrate this, you will get it. Therefore, the integral becomes the logarithm of this function. So we have here the logarithm of s cubed minus 7, and then plus the constant of integration. It's an interesting one. Take a look at how I've done that. You may meet problems like this. You just simply need to do this little adjustment to get the solution done.